This is part 2 of the tutorial about type classes. In part 1, I was talking about how to analyze a type class by combining all its methods into a single value with a certain type. And then we found that this type can be often of an algebraic form, pt to t, the co-algebraic form, t to pt, where p is some functor. Previous example I was talking about was functor, which we found to be both algebraic and co-algebraic with different definitions of p. And this is okay, so it is not necessarily a problem. That actually it is better if a type class is both algebraic and co-algebraic because it has more type derivation patterns, type class derivations. The next example I'd like to talk about is the show type class. The show type class has this signature, and it has the form t to pt, in other words, co-algebraic, where we define p as a constant functor, which always returns the string type. And that is allowed, that is not a problem to have that. So the show type class is co-algebraic, but it is not algebraic because we cannot represent this type signature in the form pt to t. There's no t at the end. We cannot change that type signature equivalently to an equivalent type signature of the form pt to t. Another example is a traversable type class. This is a formulation where, again, it is not obvious how to transform this type into something of the form pf to f or f to pf. So we need to try a little bit. And what we find is that we can transform this into co-algebraic form, fa to pfa, where p is a higher-kinded type constructor, and it is defined like this. So given a functor f, we create a new functor pf, which is applied to x and gives this type. Now notice that the type parameter x here is in a covariant position because it's under the arrow here, but also this function type is under a function arrow here. So this x is actually in a covariant position. And the type parameter b is used existentially. So it's similarly to what happened with the functor type class. We find that we are required to use an existential type to define this form of the type class. This is not a problem. It doesn't matter if it's existential there or not. What matters is that pf is covariant in f, and it is. F here is in a covariant position, and that it is also covariant in x. And it is covariant in x, so there's no issue. And so we conclude that the traversable type class is co-algebraic. Another example is the pointed type class. So pointed is where there is a method of this sort. And this has the form pfx to fx. So note here, t is an arbitrary type parameter, so we can use x instead of t if we feel like. So we define pfx to just be x, and then we get this type signature. So the pointed type class is algebraic. P is the identity functor. It does not depend on f, which is fine. So it is still covariant in f when it doesn't depend on it. And so the pointed type class is algebraic. The final example is the equality type class, which has this method. And we find that we cannot write this method type either in the form pt to t or in the form t to pt. Now we can write t to pt, where pt is a function t to bool, but that's not going to be covariant in t. And so that is not of a co-algebraic form. So this type class is neither algebraic nor co-algebraic. The practical consequence of this is that this type class will not have such a rich set of type class derivations, which type class derivation could be possible for this, but it would have to be implemented ad hoc, not in a generic way like in all other type classes. And most of the theory that I'm going to show here will not actually apply to the equality type class. So it does have certainly some type class derivations, but they will have to be considered specially, and laws will have to be proved. So the theory that I'm going to describe in this tutorial promises to show very generic type class derivation patterns and automatically satisfy the type class laws. And that is not going to be the case for the EQ type class. At this point, it is interesting to have an overview and a little digression to look at how type classes are related to other design patterns in programming, namely algebraic data types and object-oriented interfaces. So I will just have a short digression about that right now. So let's look at how algebraic data types are defined. So one way of defining them in Haskell is to use this syntax. So I call it the long syntax, where you separately declare each constructor with a full type signature. So the function C1 takes an int value and returns a value of type G. And the function C2 takes a bool value and then another value of type G and returns again a value of type G. So similarly, we can gather all those constructors into a single type signature, and it will be of the form PG to G, because you notice that all the constructors of an algebraic data type must be functions whose final output type is G, is the type itself. And so we can gather all the arguments by currying here, and then we can have a coproduct type that unifies all of those arguments into one big value, from which we have a function to G. And so then we have a type signature of the form PG to G, where for this particular example, P is defined like this. So it's a single type signature that describes all constructors at once. And so then we can say, so the algebraic data type G is a type that supports a value of this function type. So this is a structure map of the algebraic data type. And this is similar to what happens with type classes. Type class is described by saying that the type T belongs to the type class if there is a value M with a certain kind of type that depends on T. So here we say G is a type that supports a value M of this type. So this is an algebraic type signature. So an algebraic type class is very similar in spirit to an algebraic data type, except that, of course, an algebraic data type declaration defines a specific type and not just an instance of a type class, but it could be very easily transformed into that, into an instance of a type class. And then it will be a type class that has these methods of working with G constructors and possibly has other methods, which we don't know about. So in this way, we see that the type classes, the algebraic type classes, are very similar in spirit in the type signatures to algebraic data types. Now let's take a look at the object-oriented interfaces, how they are implemented. So for example, in Scala, you would write a trait. So that's the keyword for object-oriented interfaces. And then you would say that there are two methods, say, of these types. So the method f1 returns a boolean. But what does it mean? It returns a boolean. It takes a value of type G and returns a boolean. So actually, it's a function that has an argument of type G, which we're not writing in this syntax, and returns a boolean value. I believe in Scala the syntax is boolean, not bool. I will fix that in the slide. And the second method takes an integer and returns a value of type G. But actually, so that's what we write in Scala, but actually, object-oriented interfaces always have this implicit first argument, which is of the type that we are declaring. And so actually, from the point of view of type theory, you have to write out this first implicit argument, which is G. So then the function f2 actually has this type signature G to int to G. So similarly, we can gather these two function signatures into a single type signature of this form. And the first argument is always going to be G. So we uncurry everything as much as possible. So to get the first argument, which is this implicit object-oriented argument, in Scala it's called this. So this is always available when you declare these functions. And so actually it's an argument which you have to write out when you write down the type theory view of these functions. And so then you have combined the type signatures of all methods in the interface into a single type signature of this form, where P, for this example, will be defined like this. So we have uncurried, and then there's this function. So P is a type constructor that unifies the types of these functions. So essentially bool, product of bool, and this type, int to x. And then there's a implicit this argument. So then this is a co-algebraic type signature. So an object-oriented interface describes types G that support a value with this type signature. So it's very similar to a type class that has a co-algebraic type signature. It's a value of the same kind of shape, provided that P is a covariant functor. This is not always the case with object-oriented interfaces, because you could have here G also, and then you will have Px equals, here you will have x to x, and that's not going to be covariant. But in case it is covariant, in case these methods do not take arguments of type G, but only return the type G, then it's going to be co-algebraic. So this is the connection between type classes and algebraic data types and object-oriented interfaces. In some sense, the type classes generalize both into a single design pattern in the language. So if your programming language has type classes, then it has both features to support algebraic data types and object-oriented interfaces. Although, like I said, subtyping is not necessary for type classes to be used. So object-oriented interfaces are designed to work with subtyping, but it is not necessary. You can have similar benefits without subtyping just by using type classes, because you have a possibility to define a type class with co-algebraic type signature or with algebraic type signature. And so in this way, type classes can be seen as a generalization of both algebraic data types and object-oriented interfaces. So they can help to mitigate the expression problem. And also, if you have a problem domain where you have mostly algebraic type signatures or mostly co-algebraic type signatures, then you can use type classes to model both. You don't need in your language to have object-oriented inheritance. in order to do that. So now that we have discussed the examples of type classes of algebraic and co-algebraic forms, the next step is to look at derivation patterns. So this I will do in the next part of this tutorial.